Okay.
This is what I would ask students to do, is to, before we get started, I very, very seldom start with definitions. 341, what is the law of reflection?
That states that the angle of the incidence is equal to the angle of reflection.
Whatever the deuce that is.
Now, what does normal mean?
And what does normal mean? Well, you know what? Let's ignore the book for a moment.
Okay.
Normal is a line perpendicular to a surface at a point on the surface. So our normals
normal
we have
force.
perpendicular. All right, but it's really important here this at a point on the surface, because some things are flat, so the normal is going to be perpendicular to that, but some things are curved, and so a normal on a curved surface is going to point in different directions depending on where you are on the surface. So this is a basic important idea for optics. All right, so we have to have some definitions, and incident means incoming. You've got a surface, you know, and I'm going to start doing this now. Here's a surface.
Nope.
Got it hang. All right.
Do you like my new location for the rulers over there?
Yeah, I spotted that.
Yeah. I was like,
Okay,
that's
and
not
then,
working
so
there.
I'm going to use this protractor to make a normal. And if I have a light ray that comes into the surface, that's incident. Okay, reflected is bounced back from a surface. So if it comes in like this, then it's going to go out like, well, I'll just, all right, hang on a second. I'm going to measure this angle. This is 38 degrees over here. I'm going to measure 38 degrees over here, and I'm going to draw another. That's the reflected. Okay, so now refracted is a ray that bends and it passes through a surface. If you look through my glasses, notice it looks like I have a dent in the side of my head. There's no dent in the side of my head. But what it is the light passing through the surface bends. So let's draw another one here. And this is refracted. Now notice it reflected and refracted. R-A-L-E is the only difference. So I use reflected as R-L and refracted as R.
Or refraction, no, I'm just kidding.
Refraction, that's great. Okay, so here's some basic things we have to do. Now, do you know how to use a protractor?
For the most part.
You have to line things up properly if you're going to, well, this is for students, you know, they don't know how to use protractors.
In the middle there.
What you want to do is you want to measure the angle from the center point. Years of markers on this. Okay, and you measure the angle like this. So you read the angle out here on the outside, but it has to be at the vertex. It has to be at the crosshairs that every protractor has in order for it to be legit. Okay, and there's two ways to do this. If you have an angle like this, you could measure this angle or this angle.
Yeah.
And the way you make the measurement, I mean, 70, 110 degrees, those are different. You need to know how you're going to make these measurements. Okay, the law of reflection says the angle of incidence equals the angle of reflection. You've got the incident ray comes in and the reflected ray goes out. And so, let's see, let's use red and blue here. Here, the angle of incidence is measured from the normal. So this is the angle of incidence. It's measured from the normal, and this is the angle of reflection. Okay, you don't measure it here, you don't measure it here, you measure it from the normal. Now, why is that? The surface is not always flat, and sometimes it's curved.
Can measure from the outside if it's curved.
Yeah, yeah. Well, you measure from the tangent. All right, here's looking at you. All right, so what we're going to do is this. Okay, reflection on a plane mirror. This is a plane mirror, P-L-A-N-E, it's flat. Okay, it's on those like little Twix or something like that. And what we're gonna do is, this is called the optical disc. And what it is, it's a protractor with no numbers on it.
Ah, okay.
Okay, and what we're going to do is place this on there, and we're going to use this cover that has, now there's two, this is a light box, this is a power supply. Inside the light box lives a light, and it works much better when it's plugged in.
There it is.
Okay, now notice the light coming out of this and the light coming out over here. Okay, this has a lens inside of it. This doesn't. So what we're going to do is we're going to do this, and notice that what we get is a straight line. All right, I'm going to move over here. Okay, so the idea is this is the normal here. And what I want to do is have light that comes in at this point right here, hits exactly in the, at the vertex. Okay,
right there.
So this is the angle of incidence right here. It's 10, 20, 30. So on our first one here, it's 30 degrees. So here we've got the angle of incidence is.
Oh, I see. Oh. So the kid put it back and didn't freaking tell me, Miss Moore, it's broken. Kid's like, Miss Moore, can I keep this? Yes. Those are literally all for you.
Okay, so that's 30 degrees. So it comes in and it bounces off the mirror and is reflected over here. And that's 10, 20, 30. So that's 30 degrees.
Boom.
Okay, let's try another angle. How about this? This is 10, 20, 30, 40. That's 50. Well, let's try 45 degrees. Okay, I'm going to try to come right over 45 degrees. I want to hit right exactly on the center there.
Oh, look at that.
And so here's the angle of incidence, and I'm missing it a little bit here.
I see.
So let me just adjust this so I can get it right over that and right on the center. There it is. Oh, no, it's not. So you got two things. You got to have this in the right spot, and you got to hit that on the right spot. So let's see if I can do that. Boom.
Look at that.
Okay, so the angle of incidence is 10, 20, 30, 45 degrees. The angle of reflection, 10, 20, 30, 45 degrees. So 45 degrees in, 45 degrees out. And the question is, does this observation support the law of reflection?
And the answer is yes.
Yeah.
Absolutely. Because the law of reflection says that the incident wave will be equal to the reflection. The wave, what is it? The
ray.
Ray.
Light ray. Okay. And then it says, put a scrap of paper in front of the surface of the plane mirror and shine the beam of light on the paper. Is there a reflection? Okay, this always confuses students because you've got the reflection here, and then you put, and you're gonna have to get up in order, or come over here on this side. So you put it on it and they say, oh no, the reflection goes away, but I notice, see see how dark it is right there? And then it's not?
Yeah, there is a reflection.
There is a reflection, but it's not like a sharp, regular reflection. It's like spread all over the place, okay? So the light reflects off of this, but it produces a different kind of reflection. Let's talk about that.
So,
there's two kinds of reflection, regular and diffuse, and it's a spectrum. There's a range. If you have a shiny surface like a mirror or a wet road at night, that produces a regular reflection. You can see the lights from the headlights of the car is bouncing off of the wet street coming toward the camera here. A diffuse reflection is produced by a rough surface. Okay, so a regular reflection, regardless of what kind you have, it always obeys the law of reflection. Here's, this is Mark Cavendish, and why is the skin chewed off of his thigh like this?
Because he fell on the road. Oh.
And what about the road?
The road is rough.
The road is rough. It's like a cheese grater. That's right.
Yeah.
This guy's one of my heroes. By the way, your mother, I'm sure, has heard of Mark Cavendish.
Oh, I'm sure.
Anyway, so what you have is, on a regular surface, you have the law of reflection, law of reflection, law of reflection. Incident is equal to out. On a rough surface, you don't have, you've got all these different angles. So you have this one coming in, and here would be the normal, so the law of reflection in, the law of reflection out. Here we've got a surface that's like this, so the normal would be here, the law of reflection, and same thing here. So the law of reflection always applies, but if you have a smooth surface, you get a regular reflection, comes in like this, goes out like that. If you have a rough surface, it goes all over the place. And a rough surface is important because it allows you to see the road at night. What's happening is the light is shining on the road and the surface is rough, and some of that light is reflecting back into your eyes. Some of that light is reflecting back into your eyes. It allows you to see the surface. And you've got these lines that are have reflective material put in with the paint, so that it also shines the light back into your surface, into your eyes.
Optics.
However, if this were dark at night, you would not be able to see the road. And so these are called Botts dots. They were named by a Caltrans engineer named Botts in the 1960s. And they're called Botts dots. And you've seen them, they're in the road. And why are they there? Well, they do two things. First of all, if you drift out of your lane, right?
They let you know.
Yeah, and but at night, I mean, here it's daytime, even though it's overcast, but you can't see the road because the light from the headlights, well, here's your car, and here's the headlights. The light would be reflected like this, and you would not be able to see the road.
Because there's water on it too.
Yeah, because now you've got a regular reflection. You don't have that diffuse reflection where some of it is reflected back to your eyes. So these Botts dots, when it's raining and it's at night and you can't tell where the road is, tells you where the road is.
Yeah.
All right? Okay? Now that's reflection. Let's talk about refraction. Light bends when going through a surface, like my glasses. Okay, so here we have a surface between air and plastic. Let me grab a piece of plastic here. Here's a piece of plastic. And when light goes into this surface, when it passes through, it bends. All right, so we're going to be making ray model diagrams.
Whoop, whoop.
And here's what you start with. You have a surface, you'd say it's air on one side, plastic on the other, and then you use a protractor to make your normal. And so here we've got an incident ray that comes in at a particular angle, and here you have the reflected ray that now is at a smaller angle. This is bent toward the normal. If it didn't bend, it would go straight through like this. It would go straight through like this. So this is bent toward the normal. And there's an angle of incidence and an angle of refraction. And so these can be measured using protractors. And the angles are important. Okay, what's different here?
It's bent away from the normal because it's going from plastic.
The reason for that is before we went from air to plastic, now we're going from plastic to air, and that would be the light comes in here, goes through, comes out the other side, and now the next boundary between the two media is this surface right here. So it's going to bend in a different direction. So here's the angle of incidence, here's the angle of refraction, and it's larger than the angle of incidence. Okay?
Oh.
Okay, so we're going to do a lab right now.
Okay.
And the question is, we're going to shine light through this block. And we'll see the light come in, go through, and come out. But then when we turn the light out, how can we know where the light was? All right, so this one is entitled Light Gets Bent.
Oh yeah, what else did you? What other questions do you have on there? How does it replace the scrap newspaper and management? Oh, okay, gotcha.
See, now what I'm going to do is, no, I'm not going to do that. All right, I'm going to put this down and trace it like this. And then let me go get a protractor. I'm assuming you're on the same spot.
Yep.
And what I'm going to do is I'm going to draw a normal on here. Now first, let me extend this line out. So I put this on 90 degrees, and I'm going to draw a dot, 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 dot. There's my normal.
Bada boom.
Okay, so now we put this back on it. Is that the right side? Yes.
Nicely lined up.
Okay, so what I'm going to do here.
So incident ray coming in. Okay, cool. So we have some reflection here.
That's an excellent point.
And then we have like multiple refractions.
Okay, so see this straight line right here? That's going through underneath the block.
Oh, I see. And then you can see the reflection.
That's actually underneath the block.
Got it. So we're going to ignore that. You see that? It's got a little internal.
Yeah. Okay, so what I'm going to do is I'm going to put a dot right there.
Okay.
I'm going to put a dot right there. Put a dot right there. And I'm going to put a dot right there.
So whenever you have this sort of, do you always have, if you have an something that light can go through, do you always have reflection and reflection?
It depends on the material.
Yeah, it depends on the material. Okay.
It's like glasses have an anti-reflective coating put on them.
Yeah.
And so what I'm going to do now is I'm going to draw this line. And it came out right here. I'm going to draw this line. And then it went in this direction.
Mm-hmm.
And I'm going to draw this line.
Boom.
Okay, so now this is the path that the light ray took. All right, what does it say here? Placing no, move the block and trace the path of the beam. Okay, what happens to the beam as it passes from the air into the block? Well, if it were going straight, it would go like this.
Mm-hmm.
But what does the beam do?
It bends towards the normal.
It's bending toward the normal.
Mm-hmm.
Okay, so you got this angle.
And that angle.
And you got this angle. And then what happens to the beam as it passes from the block into the air? Well, let's draw another normal here.
Yeah, so I think we need a new normal there. And it bends away from it.
All right. So, yeah, so now, so this is an angle of incidence. I'm drawing it upside down for you. This is an angle of refraction.
Mm-hmm.
But this is an angle of incidence. And this is an angle of refraction.
Yeah.
Okay, now, anytime bending takes place at the boundary. So you got this boundary, you got this set of things. You got this boundary, you got this set of things. Okay? So let's take a moment and go back over here. So now we've shown where the light rays go after we turn off, and we get something that looks like this, yeah? And what I've drawn is I've done a normal here to where it strikes a surface, and a normal here where it strikes a surface. We've already done that. All right, so now we want to accurately measure and record the angle of incidence and the angle of refraction for both the front and the back. That's right, I use RR instead of RF.
I like the RF though. The RF is like refraction.
Yeah.
So we go back over here then, yeah?
Yeah.
So then.
So now we encounter if we, and all angles are measured from the normal. So I'm going to have to extend this line out so I can get a good, because I want this to be at 90 degrees and that crosshair to be right over the spot.
Oh, I see.
Okay, so this is measured from the normal as 10, 20, 30, that's about 32 degrees. So this is 32 degrees.
All right.
Now the challenge is measuring this one because the protractor is too big. So what I'm going to do is I'm going to lightly extend this line. Whoops. Yeah, I am. I'm going to lightly extend this line like this. Okay, now why? So that will allow me to measure this angle. So I put this here.
Now you can see
I'm going to have to extend this over here. And you can see the challenge of conveying to students what they need to do here. That's why we do this as a group activity. So that's this one. So that's about 20, it's about 19, 20 degrees. So this is, we'll call it 19 degrees. Okay, so the angle of incidence going in is
32.
Theta sub I.
Oh, no, sorry. Wait, 32? Yeah.
32 degrees. Theta sub RF is 19 degrees. 19. This is surface 1.
Okay.
All right, so now we need to do the same thing over here. We need to measure this angle of incidence. So I put this along the normal. And I'm going to have to extend this so I can do this. So now I want to measure this angle. I want to have this on 90.
Yep.
And that
right
on the
there.
crosshairs. Is that on the crosshairs? Yes. So that's about 22 degrees.
Yep.
So this is about 22 degrees. And then I want to measure this angle right here. And once again, I'm going to put this out to like this. And you can see there's some slop here, right?
Yeah.
Okay, so this is 10, 20, that's about 33 degrees.
Yeah.
So this is surface 2, and the angle of incidence is 22 degrees, and the angle of refraction is 33 degrees.
Boom.
Okay, now, what do you notice about these numbers?
They're all around the same.
They're
like,
close to each other.
Yeah.
32 is close to 33.
Yeah, and 22 is close to
19 is close to 22. And the question here is, what's the relation between the incident rate of the block and the ray that emerges?
So the incident rate of the block and
this is 32. This is 33.
Oh yeah, so their angles should be at the same, ideally.
If their angles are the same, what can you say about the two lines?
They're parallel.
Sweet.
Yeah, I was like, they look kind of parallel to me.
Yep, good observation. Okay, so now that means there must be some relationship between all these different things. So what we've got is this angle is roughly the same as this angle.
Yeah.
And this angle is roughly the same as that angle. And if we had better equipment, okay, and here's an important thing. If light didn't bend, it would keep going straight ever passing through the surface. And why is this? Because I want kids to tell me, is it bending? What direction is it bending? And so...
like it's bent.
yeah, we just did that. All right.
Sweet. Done?
We're done with